Hello there, Physics 30, and welcome to Chapter 14, Lesson 2. We're going to do Lesson 2 and 3 kind of in one here, because they're super related, and I just want to get through them so I can kind of quiz you on it and stuff. So what we're getting into is a pretty important physics principle here. It's called the photoelectric effect. All right, it tells you it's exactly what it is. It's photons creating electricity. Photons creating electricity, photoelectric effect. Right, and what it is that if you send photons onto a sheet of metal, the photons will eject an electron, which goes and creates a current. So we have photoelectric effect. All right, Hertz, by Heinrich Hertz in 1887, basically discovered this by accident, and he kind of did that by realizing that if you use UV light, you can create bigger sparks. And he's like, I don't really care about that. That's no big deal. And so he just kind of moved on to radios and never went really further with his discovery. So he kind of was the first person to prove this, but it really wasn't his big deal. So check out this video here, you guys. There's this little website. It doesn't work on my iPad, so I can't pull it up, but it does work on the Chromebooks generally. Depends on if you're updated. Check it out, the photoelectric effect. Check out the Compton effect for a little bit as well. Okay. So we have the photoelectric effect produced some puzzling results that they kind of went against the wave theory. So this is, again, we're in that period of time where we're trying to figure out, is light quantized? Number one, everyone's not quite sure. And number two, is it a wave or is it a particle? And or as Einstein says, it both. And so what we have is that when electrons hit the surface, when light hit the surface, the electrons were emitted immediately. So there wasn't time for like energy to build up or anything like that. There was a minimum frequency, that could be shown on metal that could produce electrons. So if you had anything below that frequency, no electrons were produced. Every different type of metal had a different threshold frequency, right? So you had to hit a certain frequency before it started doing this effect. And if the threshold frequency is met, if you make the light brighter, you get the number of electrons increased. And so none of these things really make sense for the wave theory of light. Okay, and you can see that here, right? If light were a wave, brightness should affect the movement of the electron. The light should be able to build up enough energy for electrons to leave. So what they thought is that if it was a wave, if they took green light and shone it on the metal long enough, it would eventually start giving off electrons because the energy would build up. What they noticed is that it doesn't matter how long you shine green light on the chunk of metal. If it's got a threshold frequency higher than green light, it'll just never give off electrons. Okay. And it was basically instantaneous, which means it doesn't have time to build up. And so this leads us to the idea that it's a particle. So Einstein, of course, did all of this, and he said, well, it's because light's a particle. And everyone's like, that is silly, especially Millikan. Okay, don't be Millikan. All right, Millikan spent 10 years basically performing sophisticated photoelectric experiments, basically trying to disprove Einstein. In the end, he was actually the one that proved Einstein right, and that's what gave Einstein a Nobel Prize. So imagine spending 10 years trying to prove someone wrong, only to discover that you proved them right, and you gave them, the Nobel Prize. Like, pretty big deal. So Millikan later, he got his own Nobel Prize in 1923. But yeah, so what Einstein's saying is that photons hit the metal. These photons would instantaneously transfer energy to the metal, allowing for the electron to escape. It was an all or nothing occurrence. If the photon did not have enough energy to knock the electron loose, then nothing would occur. So the photon came in, and if it had enough energy, it would fire an electron off. But if it didn't have enough energy, nothing would happen. It would just basically disappear, right? Or reflect, depending on. So remember, our lowest energy light is red, right? And so we have red's got low frequency and low energy. So when we send this red light in, it basically doesn't do anything. It's just hitting, and it's giving some energy to the electrons maybe, but the electrons are not getting enough energy to eject. So nothing happens, right? So we need to send in light with a different amount of energy. Now remember, if we turn the brightness up, all we're going to get is just more low energy photons. Now, it doesn't matter how bright this red light is, it just won't ever cause the electrons to release, right? So then we decide, okay, well, we're going to send in some green light. Now, green light is above the threshold frequency. So green light, when it hits, it gives off electrons, but they have low EK. They kind of barely give it off. But if you send in But for every photon of green light you send in, you get one electron coming off, right? So it's 1 to 1. This leads again to the quantization of light, the electrons, right? And just Millikan just did not like this, right? And so okay, so what happens? So now we're getting three photons come in, 3 electrons go off. 30 photons get in, 30 electrons come off, right? And this is basically it has a minimum amount. So the electrons will be emitted, but they don't really have any kind of kinetic energy because it's the minimum amount. So they're just going to come off, they're just going to come off and not really go anywhere. There'll be very, very small kinetic energy or zero. So what that tells you is that it takes work to free an electron, right? So when this photon hits, electron comes off, some energy is lost, right? Some energy is lost. Basically, the energy is lost to actually changing the photon's energy into electron's energy, and it actually stays behind in the metal, so to speak, right? And so conservation of energy still holds true, and it's actually going to follow this equation right here. And yeah, and so basically that the work function is a set amount. If the photon comes in with more energy, then the electron can leave with energy. So the work function of this, right, the work function is basically when it comes in, the work function is how much energy gets lost, right, between this process. So it comes in as a photon and then it leaves as an electron. There's energy lost in this process. Okay, it takes work to free up an electron. Okay, now for every metal has a different work function, but it's always the same. So for every photon that comes in, so if I send in a photon with just enough energy, then the electron loses a little bit of energy. If I send in a photon with lots of energy, it's going to leave it. But how much they each lose is the same. All right, again, this sticks with our conservation of energy, which is number 5 here. Okay, and what that leads us to is that, okay, well, the green light did give us electrons, but they didn't move very fast. If I shine blue light, it'll give us electrons. So I still have 1 electron to 1 photon. But what it's basically telling you is that as I increase the frequency, I'm going to increase the energy of the light of the electron coming off, right? So this is the photoelectric effect. Okay, again, please note that this can't just build up. If the red light is shown on this metal, it doesn't matter how long you shine it, it'll never, ever, ever release an electron. Just because those individual packets, those individual quantized photons don't have enough energy to release an electron. Okay, so this is the photoelectric effect. These are kind of the main things, right? Brighter light gives off more photons, which means give off more electrons, but doesn't change the speed of the electrons or the kinetic energy electrons. Maximum kinetic energy electrons is dependent on the frequency of the photons that are absorbed, right? So if I change the photons and the frequency of the photons, we're going to change the kinetic energy. Okay, anything below the threshold frequency, anything below that work function, is not going to free any photons. And as photons, energy is delivered in packets, and there's no time delay for the energy to gradually gain, the electrons to gradually gain energy. They're either absorbed, or they either absorb the photon or they don't. So these packets of energy are hitting the electron and actually changing the electron's energy level. Okay, so here is the work function, or known as the threshold frequency. Okay, so this here is the work function, and this is the threshold frequency, right? So any frequency below that will not give us any electric effect. Any frequency above that will give us electric effect, okay? And so that's kind of thing. And you can see that for different metals, they have different work functions, right? So it takes more energy to pull an electron off beryllium than it does to take it off of calcium, right? And it's going to be with metals, right? Okay, the work function is under atomic physics. It's right here, okay? And that's it. All right, okay, so one thing you notice again is that we deal with both joules and electron volts, and I want to show you that this is where we're going to start getting away from joules and start using electron volts more, just because it's just better numbers. You don't have to write the times 10 to the negative 19 is essentially what happens. So the example here is determine the work function of platinum, which has threshold frequency of 1.28 times 10 to the 15 hertz. So what I did here is I got the work function, right? And it's got Planck's constant in it. If it's got Planck's constant in it, it means that we can choose either to do it in joules, using 6.63 times negative 34. Or we can choose doing electron volts, which is 4.4 times 10 to the negative 15. Right? And so if I do the work function in joules, I'm going to get this number of 8.49 times 10 to the negative 19. Perfectly fine number. But if I do it in electron volts, I get 5.3 electron volts. Right? Now, this just makes more sense to use electron volts because it gives us a measurement that makes sense, right? So these are the same answer, but they're just in different units, right? This many joules equals this many electron volts. There is no, right? This joules and this electron volts are the same, right? It's the same as how it would be weird, right? It's kind of like measuring distance from Melk River to Lethbridge, except measuring it in centimeters, right? This would be like measuring in centimeters. You could do it, you'd be right, but wouldn't it be better to measure it in kilometers, right? Okay, so it's just a better measurement when we're talking about these small amounts of energy and all that kind of stuff. So that's one part of it. Okay, so now we have to figure out, well, there's a part of this is how much kinetic energy does an electron have? How do I figure that out? How do I figure how much energy? Well, we're going to basically figure out how much energy an electron has by putting it into an electric field and basically timesing it by the Q equals V stop. So the EK max is just another way to find the EK of an electron. That's all this really is, okay? And it's more related to the next stuff we do, and you'll see that. So EK is the energy of the emitted electron. It has to be in joules, though. That's one thing. So I just spent all this time saying that electron volts is better, but this equation has to be in joules because voltage is kind of also based on joules. So this has to be measured in joules, okay? Charge an electron and V stop, and it kind of goes from there. All right, so this is how much voltage is required to stop the electron, or you can use the voltage and the charge of the electron to figure out the max kinetic energy of those electrons, right? So, yeah, that's kind of the idea. All right, this is also in your formula sheet under atomic physics, right here. Okay, it's right there, and so you can do that. So determine the stopping voltage of the electron having kinetic energy of this, right? So if I have to find the stopping voltage, I'm going to say, okay, well, I've got EK equals QV, put in the EK, 3.2, times 10 to the negative 19, equals 1.6 times 10 to the negative 19, V. You're going to divide those and you get that the V value is 2.7 volts. Okay, when you divide by those, it gives you 2.7 volts. So they would take 2.7 volts to stop this electron, right? All right, and then this one here, it gives us the kinetic energy in electron volts. Now again, we look and we make sure, okay, hold on, this here has this equation. It's very important that it's in joules. This equation breaks down if we don't do it in joules. Okay, so I got to turn it into joules. Now, as a reminder on how to turn things into joules, I have an electron volt, and I have an electron volt, and I times it by 1.6 to the 19 joules for 1 electron volt. That comes off your formula sheet, and it gives me that it's 8 times 10 to the 19 joules. When I do that, I get 5 volts, right? 5 volts. Well, that's weird. I have 5 electron volts, gives me 5 volts. And so what that tells you is, oh yeah, I forgot. Electron volts is based on how much voltage it takes to stop an electron, right? 1 EV is 1 volt stopping 1 electron. 5 EV is 5 volts stopping 1 electron, right? So it makes stopping basically this next thing, right? So that makes sense. So this is, if you have something in EV, right? If you have the energy in EV, then this V stop is the exact same, and that's the way it works. So it's kind of interesting that way. Okay, so that's practice problems 9 through 16. All right, that's practice problems 9 through 16 is those ones. Okay, now we're going to get into this equation here, which is E photon equals EK of the electron plus the work, or EK. So this comes from the conservation of energy, and what it's saying is that they have this is based on, remember in physics 20 we always started with this, E initial has to equal E final. That's the conservation of energy. In this system, the initial system, we have just a photon. So it's the E of the photon, right? That's initial. Then afterwards, what we have is we have the E of the electron, right? Which is an EK, right? So that's going to come off, but it's not the same because we know that we lose energy in this process. There's some energy lost in this process, and so we're going to have to account for the energy. If the energy is lost, it always goes on the final side, right? So that's one way to think about it. The other way to think about it is that the photon, and that's this, so that's that equation. Okay, so it's based off conservation of energy. This is the initial, there's just the photon. Then afterwards, there's the energy that's lost due to friction or heat, which is, this isn't friction or heat, but it's the same concept, plus the kinetic energy electron. That's one way to think about it. The other way to think about it is that the energy of the photon coming in will not just equal the electron. It's going to lose some. So we're going to take the energy of the photon and we're going to subtract how much it loses, and that'll give me the kinetic energy electron. Okay, so this formula can be split into many different things. So you gotta be careful. With the E photon, you're generally going to see it as, you know, HF or HC lambda. You will never see 1/2 mv squared or anything like that because they don't have mass. Okay, the EK of the electron is generally going to be 1/2 mv squared, but it can also be this QeV stot that we just learned. And the work is usually going to be HFO, right? And that's the work function. Or it could be the change in energy sometimes, but it's generally going to be the top things. So you're usually going to see these three, but just keep in mind these are alternate versions of those three, right? So there's a few different ways. And of course, we know that change in energy can be listed so many different ways, and we can talk about that. All right, but again, this is the EK of the electron, not the EP. All right. So different metals have different work functions. That's all that these two slides are saying. I'm not really going to go dive into them very much, right? This used to be important in the diploma, but I'm not going to really go about anything like that. Okay, yeah. All the graphs are the same except for the position where they cross the x-axis. It's because where they cross the x-axis is very much dependent on what the metal is made of and how close those electrons, or how easily those electrons are lost. All right, so here's an example. And I fill out these examples just because it kind of speeds the video up. All right, photons having energy of 3.2 are an incident. Okay, incident means it's hitting. They are incident on cesium metal having a work function of 2.02 eV, resulting in the emission of electrons. Calculate the kinetic energy electrons emitted. So kinetic energy. So we start with EFO. I just put EPH. Can't put EP because that's potential. So EPH is equal to the E of the electron plus the work. That's the equation. This is not in your formula sheet, so you do have to memorize this. Okay, which tells me then I put those numbers in, and I get EK equals 1.18 electron volts. Good, right? So I've got 1.18 electron volts is how much energy they have. But the issue with that is that I want to figure out the speed. So the speed is in this equation. Okay, electron volts can't go into our EK equation. It just doesn't work. So we have to convert to joules. So we use our conversion from our formula sheet, convert to joules, put it in, and we're going to get a velocity of 6.44 times 10 to the 5 meters per second. Okay, so what we've done here is we've talked about, we know the work function, right? And we've decided how much energy these photons have because we're choosing the frequency of these photons. And so it gives me this concept here. And then I can find the speed. So just from knowing the two things, just from knowing the energy of the photons and the work function, I can actually find the speed of these electrons. So we're not introducing a lot of new formulas, but we're linking a lot of old formulas together. Okay. All right, so light falls on a photoelectric surface with a work function of 1.6 eV, resulting in emission of electrons with the kinetic energy of this. So I have the work function and I have the kinetic energy. So E equals EK plus W, right? EFO, this should be EFO here, sorry, EFO. All right, so EFO equals 3.78 plus 1.6. So the energy of the photons was 5.38, right? So if this is how much energy the kinetic had and this is how much it lost, then the photon started with this much energy. That makes sense. But now the second part of the question, there we go. The second part of the question here. All right, second part of the question here is about identify the region of the electromagnetic spectrum where the photons belong. Okay, so when it's asking for what region, usually you're going to have, if you do have the electromagnetic spectrum memorized, which you're supposed to under normal circumstances, you would have it memorized in wavelength. So what we're going to do is we have the energy of the photon. These two are just constants, and so we're going to find the wavelength of that. And so we figure those out Okay, remember, be very important that we use the 4.14 because that's the electron volts and our energy is in electron volts, right? We do that and we're going to get 2.31 times 10 to the 7 in our calculator. You have to recognize that that's 231 nanometers, which is just into the UV light, okay? Just into the UV light. All right, so there's that question there. Again, take your time, watch what I did, understand why I did those things, okay? All right. So this one here, electrons are emitted from a photoelectric surface at the speed of, so it gives the speed of the electrons. Okay, if the work function of the metal surface is 2.12 eV, determine the frequency of the incident photons. So we got to determine the frequency. So the first step I did is I took that 5.2 times 10 to the 5 and the mass of electrons to figure out the energy of those electrons. That's the EK part, right? Now, what I noticed is when I first figured this out, I had this in joules and I have this in electron volts, right? So what I'm going to do is I have to make sure when I put them into this equation, into my conservation of energy equation for the photoelectric effect, I have to make sure that they have in the same units. So I easily converted this into electron volts. So now they're both in electron volts, I can then put them together into this, right? So I have the electron volts. So then I can figure out the photon's original energy level. Figure out the photon's original energy level, and it wants me to get to frequency. So then I can use EPH equals HF and do that, and I get a frequency of 6.98 times 10 to the 14 hertz. Okay, so it's step 1 is find the energy of the electrons. Step 2, apply the conservation of energy equation. And step 3 is then find the photon, the frequency of the photons. All right, again, I double checked my calculations, but I could make a mistake, so let me know if I did. It's very important that you guys kind of start to see these pathways. And these pathways are going to be very tough. You're going to be going through them from basically in your formula sheet. You're going to be in the momentum and energy section. Then you're going to head to the waves section, or starting the atomic physics section, and then sometimes you have to go back, right? And this is all kind of linking together. So you're bringing all of the equations that you've learned, right, about energy and what are not enough, when to use energy of an electron, when to use energy of a photon, all these things, and then frequency and wavelength, and putting them together into this kind of step-by-step process. So it's almost like a maze, right? And you have to take the right turns and use the right equations and make sure you go in the right direction, okay? So that is it for lesson 2 here. You have practice problems 17 through 27. This is actually all you're assigned for this week. You just have these 2 lessons. Okay, and then you have, of course, your mini quiz, and you can do your anticipation guide. So read questions 10 to 11 in the anticipation guide, and then read section 14 through 3 once you're done, and go from there. Okay, next week we will get into the rest of chapter 14.